For today, we have wave interactions. So maybe someone from you want to help me by reading these statements. What is wave interactions?
Because mechanical waves are not matter, but rather are displacement of matter. Two waves can copy the same space at the same time. The combination of two overlapping waves are called superposition. Ideally, the superposition principle holds true of all types of waves, both mechanical and electromagnetic. Displacement in the same direction produces conductive interference.
Okay, thank you. Thank you, Ashley. So, as in the beginning, it is mentioned, okay? Mechanical waves are not matter, which means that we cannot touch it, okay? But they are displacements of matters. That means that two waves at the same time can occupy the same space. When that occurs, okay, we have what we know as superposition. Displacement that are going in the same direction produce constructive interference. Now, we can have two type of interference, okay? We can have constructive interference, which is when the two waves are going in the same direction, or we can have destructive interference when the two waves are coming in different directions. So both constructive and destructive interference are examples of what we know overlapping waves or superposition. Superposition is just another way to say that one wave is above the other one. Mhm. So they overlap when that happens, and um, that situation is called superposition. Okay, so in constructive interference, is known as a superposition of two or more waves in which displacement on the same side of the equilibrium position are added together. In other words, here the two waves are in the same side, sorry. This is the positive side of my wave trace, and that's the negative side. So as you can see, the two waves have positive amplitudes, and they are positive because they are above the equilibrium position. Remember, when the rope is at rest, no moving up or down, we say that is the equilibrium position. And because the two waves are above the positive part of the equilibrium position, we say that those waves are positive waves. So the two waves are coming. As you can see, they have different directions. And then happens what we have in part B. They begin to overlap. Okay, this is still the first wave, and this is the second wave. As you can see the projection. So when that occurs, picture C, it's happening, okay? And that's nothing more than the two waves when they are added. I mean, mathematically, what happens in part C is just an addition. I took the amplitude of my wave 1 plus the amplitude of my wave 2, giving me as a result a total different amplitude that is nothing more than adding amplitude 1 plus amplitude 2. That's what it means. That procedure that you see right here is what we know as superposition of waves. And because it is a positive interference, it is positive because the resulting wave is taller than the initial wave. You can see the difference, okay? So when this occurs, you can say that we had a constructive interference. Now, after the overlapping process occurs, the two waves continue in the same direction that they had before. The second wave continues going in the left direction, and the first wave continues in the right direction with the same amplitude that they had initially. As you can see, both amplitudes are still positive. But here, in this part, okay, the resultant wave has an amplitude that is more than any of them. So that way over there, in that precise point, that wave is more than the other two. Or we can say that this wave 3 is the result of adding wave 1 plus wave 2. I know 1 plus 2 gives me 3, but that wasn't the reason. Okay, so I can call wave 3 is going to be equal to wave 1 plus wave 2. That's what it means. Now, this method of adding the waves or the displacement of waves is known as superposition principle. Okay? According to this principle, when two or more waves travel through a medium, the medium here in this example is the rope. Okay, so the two waves are traveling in the rope. So when those two waves or more than two waves are traveling through the same medium at the same time, the resultant wave is going to be the result of adding the individual waves in that precise point. Now, the other type of interference is what we known as destructive interference. So take a look to the image. I will read it to you. It says displacement in opposite directions produce destructive interference. In other words, you have a wave that has a positive amplitude and you have a wave that has a negative amplitude or an amplitude that is below the equilibrium position. When this occurs and the two waves are traveling in opposite directions, you can see the positive waves going to the right and the negative one is going to the left. When that occurs, and also the type of amplitude. One amplitude is positive while the second one is negative. Okay? So when this occurs, there is a point where the two waves are going to overlap. So this, let's call this the instant before. So this is the wave that is below the equilibrium position, and this one here is the one above the equilibrium position. So they're still the same waves. This is still number one, and this is the number two. So there in that point is where they begin to overlap. When that occurs, the resultant wave. How is the resultant wave compared uh, to the resultant wave that we had in the slide before? Take a look. In the slide before, we have the resultant wave that was this tall, okay? That is the resultant wave. Now, let's take a look to the new wave. This wave, if you compare it to the one that we had before, is smaller in size. And the reason is because in a destructive interference, because you have a positive and a negative wave, Instead of adding, what you're going to do mathematically is that they are going to be subtracted. It's like when you have, for example, um, 2 plus 3 in math. When you have 2 plus 3 in math, you apply the law of signs, okay? You tell that when you have two numbers of the same sign, you're going to add the numbers and you're going to just write down the symbol, just like I did over there. But when you have the same two numbers, 2 and 3, but one of them is negative, when you have different symbols, you perform actually a subtraction. And you write the sign of the number with the greatest absolute value, which in this case is 3. So as you can see, even though I'm performing almost the same operation, in the end, what defines the result is gonna be related to the sign. Okay, here the two numbers are positive, and there I have a positive invisible sign here and a negative sign over there. So this defines that in the end, what you are doing is just a subtraction of the numbers, and here you do an addition. Same happen here in the waves. Because you have a positive wave and a negative wave, what you perform actually is just a subtraction. So destructive interference is a superposition of two or more waves in which individual displacement that are opposite in opposite sides of the equilibrium position are added together to form the resultant wave. Yes, they are added. Even though it looks like, because it is a subtraction, but in the end, this is added. Like, for example, here in math, again, I can also write the same expression that I did before. I can say that I'm going to add negative 3 to this number 2. In the end, the two operations are addition. But in this case right here, I'm adding a negative symbol. So I have to follow the instruction that when you add negative symbols, you in the end, you subtract and you copy the symbol of the greatest absolute value. Yes, they are both additions, but one of them has to follow the principle, the law of signs. Same happens here in destructive interference. Now, a wave can be reflected. So take a look to the boundaries that we have. We have a free boundary and a fixed boundary. In a free boundary, this example is like when you just don't want that your dog runs away, for example. So what happens? Your dog is free to move. You attach him to with a rope to, for example, a tree. Okay, the dog is free to move. But in the other hand, you have a fixed boundary. A fixed boundary is more like a fixed position. Okay, so in this point, take a look to what happens here. I'm going to show you a video, so don't get frustrated if you don't understand the point yet. Okay, because afterwards I'm going to project a video. Now take a look here. I had a wave that is coming in the right direction. Remember, this boundary is free, which means that the wave is free to move through the rope. So the wave is moving, okay? So in this portion, in this part of the free boundary, the pulse is enough to move the free end up. And after this occurs, the knot is sent down and the wave is being reflected. So it was initially going to the right, and now you have the same weight that is going in the opposite direction. Now, after this occurs, we call this the reflection of a wave. Okay, so the wave moves to the right, the reflection is going to move to the left. So, at a free boundary, waves are reflected. Now let's see what happens in a fixed boundary. Fixed boundary is an end that doesn't move. Okay, so the rope in that end is never going to move. It's going to be totally fixed. So in this case, the wave is coming to the right, but once it hits the fixed boundary, it's not able to move the rope up or down. Okay, so it's totally fixed. It's totally fixed. But still, the wave is being reflected. But in a fixed boundary, the reflected wave is in the opposite position. What we see right here is the reflection of the wave, just like we did before, is going now in the opposite direction, but also is inverted. So this happens, the inverted reflected wave happens only in fixed boundary. While in the free boundary, it's just reflected. It continues always in the positive side, for example, in the same side that it was coming. And here it's coming from a positive side to a negative side. So you see, that's the difference between the two type of boundaries. Okay, so you can have free boundary and fixed boundary, and the reflection is going to depend on the kind of boundary that you have. Now, all I said, it's nice. I mean, this is a summary that I did. It's all I say is nice, but it is better when you watch a video. Okay. So from now, I'm going to project a video where you can see what I'm talking about. I'm going to be stopping the video every like 10 seconds, so I'm sorry about it, but I'm gonna be explaining like what is going on in the video every couple seconds.